Hello everyone and welcome to this lecture on k-nearest neighbor algorithm. As the recap, so far we have discussed two broader categories of supervised machine learning, which are regression and classification. We also discussed what do we mean by training data and testing data. We have also seen linear regression method for linear regression problems and the corresponding implementation in Python. In today's lecture, we will try to cover the k-nearest neighbor algorithm, and we will also discuss one example to see the inner working of the algorithm. The k-nearest neighbors algorithm is a simple yet powerful machine learning technique used for both classification and regression tasks. It operates on the principle that similar things exist in close proximity. In a sense, KNN looks at the k nearest neighbors of a data point and predicts the class of the point. The algorithm does not require any model to be built in advance. It is highly intuitive and easy to implement, yet its performance can be significantly improved by the choice of the k, that is, the number of neighbors we are considering, and the distance matrix used to find the nearest neighbors. To check the nearest neighbor, Euclidean distance is often used as a distance metric. There are other distance matrices as well. Let's consider this example. Let's say the problem at hand is that given the two independent variables, wind speed and temperature, we want to predict the corresponding value of y, which is discrete in nature. That is, this y can take the value either yes or no. This is a standard classification problem. If we try to plot this graph, then it might look like this, where wind speed is on one axis and temperature on another axis. The red circles represent a no instance and the green squares represent the yes instances. If this scenario is given to us and if we plot it like this, now let's say that there are a few unseen examples showing here as the blue triangles. The problem statement here is that given the already data set, which we already know, what is the class of these three triangles now? Whether they belong to the red colored nose or they are the green yes examples. The intuition of k nearest neighbor is that if you want to identify the class of unseen examples, look at the neighbors. So for the first case, if we check the neighbors of this specific example, unseen example, we can see that majority of its neighbors are nose, represented by red circles. So we can also conclude that the class of this blue triangle is also no. Why? Because its neighbors are all no. Similarly, if we look at the neighbors of this another instance of unseen example, we can easily assign this a class yes based on the values of its neighbor that we already know. However, in some cases, it is not very straightforward, like in this case, where we can assume that half of its neighbors are no and half of its neighbors are yes. But overall, this is what k nearest neighbor algorithm does. It checks the neighbors, and whatever the class of majority of the neighbors, it assigns the same class to that new unseen example. This was the visual illustration. Let's try to do that mathematically. Before going into the example of k nearest neighbor algorithm, let's see the formal definition for the same. In k nearest neighbor, k is a parameter which tells you how many neighbors you want to check. So we have to define the value of k beforehand. Usually an odd number is taken, and 3, 5, 7 or 9 are the very common choices for k nearest neighbor algorithm. Then we take the example that we want to test. Now for this t, we do not know its class. Either it is a yes example or it is a no example, or if there are other class definitions, to which class this t belongs. So what we do is we try to calculate the distance, usually Euclidean distance, of the test sample t with each of the examples available in my training data set. Out of all these examples, we take the first k examples, k being the parameter of the algorithm. So first k examples which are closest or nearest to my sample test t. Then finally I check what is the majority class of my neighbors. If the majority of my neighbors belong to yes, then the class of this t will also be yes. If it is no, then the class that I will assign to t will also be no. Let's see one example. Let's take this example where we want to predict the quality of a food product on the basis of two independent variables, the amount of preservatives in the food and the amount of color in that food product. So I have this data set, which is my training data, already available to me. On the basis of this training data set, I want to identify that for a new food product, if the amount of preservatives is 3, the amount of color is 7, then what is the quality of that food product? Either it is bad or it is good. I have to make the decision only on the basis of the previously given training data set. Let's see how k nearest neighbor algorithm works in this scenario. So as the algorithm says, we will first decide the value of k. In this case, the value of k is 3. Then for my test sample 3, 7, I will calculate the distance of this point from all the points available in my training data set. So I will calculate the distance of 3, 7 with 7, 7. The distance turns out to be 16. 7, 4, 25. 3, 4, the distance is 9. 1, 4, the distance is 14. They represents the Euclidean distance, the square of Euclidean distance. To make it more clear, let me show you one example. Let's say I want to calculate the distance between 3, 7 and 3, 4. Then the Euclidean distance would be, the d square would be the difference between the x values and the other coordinate, where this is my x1, y1 and this one is my x2 and y2. So if I try to calculate the distance, it would be 3 minus 3 square plus 7 minus 4 square. This would be 0. This would be 3 square. So the distance square would be 9. That's why the value here is 9. So once I have calculated these 4 distances with my test sample 3, 7, I will check which of the 3 are nearest to me. The nearest is 3, 4. So I have written 3, 4 here. The next one is 1, 4. So I have written 1, 4 here. And then 7, 7. So I have taken here 7, 7. Why exactly 3? Because we have assigned the value of k is 3. Means we will check only the 3 neighbors which are nearest to my test sample on the basis of the distance that we have calculated. The next part is, let me see what is the class of these neighbors. So 3, 4 the class is 7. For 1, 4 the class is also good. Sorry, in the previous case the class is good. Next case also the class is good. And for 7, 7 the class is bad. So majority of the class here is good. Out of 3, 2 are good, 1 is bad. So I will assign my test sample 3, 7 the class good, because this is what the majority of the neighbors are telling me. So this is the KNN, the k nearest neighbor algorithm. It is very simple and very easy to implement. Now, what is the next step? Like any supervised learning, the next step is to test the performance of the algorithm on unseen test data. In the case of k nearest neighbor, if you find that the performance of the algorithm is not satisfactory, then we usually try to change the value of k, the number of neighbors. As I told you earlier, we might use a different value of k, 5, 7 or 9. We can also try changing other distance matrices. In this specific case, we use the Euclidean distance, but we can also rely on other type of distance matrices like Manhattan distance. So in summary, we discuss in this lecture the k nearest neighbor algorithm. We also saw what is the concept of neighborhood or similarity. Distance measures like Euclidean distance, they supply you both whether 2 points are neighbored to one another, or in other terms, how similar are they. The lower the distance is, the similar are they in their nature. Now we will look into the implementation of k nearest neighbor algorithm. Hello everyone. In the last lecture, we discussed the theory of nearest neighbor classifier. In this lecture, we will start from the implementation of this algorithm and we will see a few examples. Let's start. So as you can see on your screen, the first step is to import the necessary libraries. In the second case, we are assigning values to our X matrix. These values 7, 7, 7, 4, 3, 4 and 1, 4, they are from the same example that we discussed during the theory of this classifier. So when we run this code, it will create an X array with 2 columns. As you can see, its shape is 4, 2, means it has 4 rows and 2 columns. Next is, for each row corresponding to X, there is a corresponding Y value. It could either be bad or it can be good. As you can see, the shape of Y is a vector of size 4. The next step includes defining the k nearest neighbor classifier, but before that we have to set the value of k. In this specific case, the value of k is 3, and using k neighbors classifier, we can create a classifier. Let's run this code. So we have created a k nearest neighbor classifier with the k value 3, as well as we have fitted the existing data x comma y on this classifier. We have given the name knn. Let's try to test it on the test sample. First, we have to create a sample which is 3, 7 in this case. We are calling it x test. And the next step is to predict the value of y for this value of x. As you can see here, there are two possible choices, bad and good. For this specific value of x, it has predicted that it should belong to the class good, not the class bad. Let's see a rather elaborate example. In this case, we will take the iris dataset. Iris dataset is a famous iris flower dataset. It has 4 independent variables and 1 dependent variable. The dependent variable y has 3 classes. We will see this in using the code here. Let's first mount the drive from where we can fetch the data. So drive is already mounted. Let's now import the necessary libraries. Next step includes giving the exact path of the data. So as you can see, the data is available in the file iris.csv in my Google Drive. As we run it, we will see a few rows using data.head function and the size of this data set using data.shape. As you can see here, it has 5 columns plus 1 column that tells what is the class of the corresponding flower. Here the ID, the first column, is not very meaningful. It just gives us the series or numbering of the data set. These are the meaningful columns: the sepal length in centimeter, the sepal width in centimeter, petal width and petal length, and petal width, and the corresponding species of the iris flower. The size of the data set is 150,6. It means it has overall 6 columns and 150 rows. Let's see what are the different classes available in the column species with the help of one plot. When we run this, we get this plot. As you can see here, this plot tells us that there are 3 categories of iris flower. One is called setosa, and our data has 50 records of this class. Second category is versicolor, and we have 50 records of that also. The last category is virginica, and this class also has a total of 50 records. So 50 plus 50 plus 50, we have a total of 150 records for all the 3 classes. Now as we move further, it is obvious that the column ID is not very important for the prediction purpose, so we will delete it from the existing data. After running this code, you will see that the ID column has been deleted and rest of them remain same. As we have done in the previous lectures also, we remove the y or dependent variable values from the x set and we keep that in a separate vector. So using this code, we achieve the same thing. The next step includes dividing our data into training and testing data set. Once again, we have taken the size of tests as 10% of the overall data set, which means out of 150, we will have 50 samples for testing data set and remaining 135 for training data set. Once we have divided our data into training and testing, next step is to create a classifier and then supply the training data to that classifier. Once again, we have taken the value of k as 3. Now the next part includes first predicting the performance of this KNN classifier on the training data set itself. We have made the prediction using this code. Now let's check the accuracy. Accuracy here means how many of the predictions are out of training data set are same as that of in the original training data set and how many of them are dissimilar. After running the code, we get this value which represents that 95.55% of the samples of the original training dataset are correctly classified by this classifier KNN. Let's try to check the performance of this classifier on the test dataset. Remember, our test dataset contains a total of 15 rows. When we run this code and check the accuracy between the actual test values and the predicted test values, it turns out that the accuracy is 100%. Means our classifier can accurately predict all the samples which are available in our testing data. So it seems like a good classifier, at least for this iris dataset classification problem. Next, we will move to the theory of decision trees.